Microchips, also known as integrated circuits, ICs, are the tiny yet powerful components at the heart of virtually every modern electronic device. From smartphones and computers to cars and medical equipment, microchips drive the technology that defines our lives. Their production represents one of the most intricate and precise manufacturing processes ever developed, combining advanced science with meticulous engineering. The journey of a microchip begins with a simple raw material, silicon, a semiconductor found abundantly in sand. Through a series of highly controlled steps, this material is transformed into a wafer hosting millions or even billions of microscopic transistors interconnected to perform complex calculations at extraordinary speeds. This video explores the fascinating process of microchip manufacturing, tracing each stage from raw material to finished product. 1. Raw materials. The foundation of every microchip begins with silicon, a semiconducting material abundantly found in sand and quartz. Silicon's unique properties, including its ability to conduct electricity under certain conditions, make it the ideal material for creating transistors and circuits critical to microchip functionality. Silicon is extracted from silica sand through a high-temperature reduction process in electric arc furnaces. The raw silicon is then refined to achieve an extremely high level of purity, known as electronic-grade silicon, with impurity levels below 1 part per billion. This purity is essential to prevent defects in the final microchips. The purified silicon is melted and then formed into large cylindrical ingots using techniques such as the Czochralski process. During this process, a single crystal of silicon is used as a seed to ensure the entire ingot forms as a uniform crystal structure, crucial for chip performance. The silicon ingot is sliced into thin wafers, typically less than a millimeter thick, using precision, diamond-tipped saws. These wafers are polished to a mirror-like finish to eliminate surface irregularities, ensuring a defect-free base for further processing. While silicon dominates, other materials like gallium arsenide, silicon carbide, and indium phosphide are used for specialized applications, such as high-frequency or high-power devices. These materials provide unique properties tailored to specific needs in aerospace, telecommunications, and energy industries. The transformation of raw silicon into polished wafers marks the first critical step in the microchip manufacturing process. This material serves as the canvas upon which intricate and powerful microchip designs will be etched, showcasing the incredible potential of modern technology. 2. Wafer fabrication. Wafer fabrication is the next critical step in microchip production, where purified silicon is prepared into thin, circular slices, called wafers, that form the base for integrated circuits. This process ensures a flawless and uniform surface on which microchip components can be built with nanometer precision. Purified silicon is melted in a furnace and formed into a single crystal ingot using the Czochralski (CZ) process. A seed crystal is dipped into molten silicon and slowly pulled upwards while rotating, ensuring the formation of a perfect crystalline structure. These cylindrical ingots are typically 200 millimeters, 300 millimeters, or even 450 millimeters in diameter, with larger diameters enabling higher chip yields. The silicon ingots are sliced into thin wafers using diamond-tipped wire saws to achieve consistent thickness. Each wafer is only about 0.5 to 1 millimeter thick, but it must be exceptionally uniform to support advanced photolithographic processes. Sliced wafers undergo chemical mechanical polishing, CMP, to achieve a mirror-like, ultra-smooth surface. Polishing removes microscopic imperfections that could interfere with the precise etching of circuit patterns. Wafers are meticulously cleaned to remove dust, residues, and contaminants using a combination of chemical solutions and deionized water. Even microscopic particles can cause defects, so strict cleanliness is maintained throughout the process. The polished wafers are inspected using advanced metrology tools, such as laser scanners, to ensure they meet strict specifications for flatness, thickness, and purity. Wafers that pass inspection are ready for the intricate process of building circuits through photolithography and other techniques. The precision and quality of the wafer determine the reliability and efficiency of the microchips produced. This phase is critical for ensuring that subsequent steps, such as photolithography, doping, and deposition, can be executed with minimal defects, paving the way for high-performance, cutting-edge microchips. Number 3, photolithography. Photolithography is one of the most critical steps in microchip manufacturing, where intricate circuit patterns are transferred onto the silicon wafer. This process uses light to etch microscopic patterns that define the pathways and components of the microchip, enabling its complex functionalities. The wafer is coated with a light-sensitive material called photoresist, which reacts to ultraviolet UV light. This layer serves as a stencil, protecting certain areas of the wafer while exposing others during the light exposure process. A photomask or reticle, which contains the design of the circuit patterns, is aligned over the wafer. The mask acts as a template, allowing light to pass through specific areas to define the circuitry layout. The wafer is exposed to UV light through the photomask. This exposure chemically alters the photoresist in areas where the light passes through. Advanced techniques, such as extreme ultraviolet EUV lithography, use shorter wavelengths of light to achieve even finer circuit patterns, enabling high-density chips. The wafer is treated with a developer solution that removes either the exposed or unexposed areas of the photoresist, depending on whether a positive or negative photoresist is used. This leaves behind a patterned layer of photoresist that acts as a guide for subsequent material removal or addition. The exposed areas of the wafer, now unprotected by photoresist, undergo etching, chemical or plasma-based, to remove material and carve out the circuit pathways. In some cases, the exposed areas are doped with impurities to modify the electrical properties of the silicon. After etching or doping, the remaining photoresist is stripped away using chemical solvents or plasma treatments, revealing the finalized circuit pattern on the wafer surface. Photolithography is a highly precise process that must handle features as small as a few nanometers. Advanced equipment such as stepper scanners ensures accuracy when scaling down designs for modern high-performance microchips. Photolithography is pivotal in determining the size, complexity, and efficiency of the microchip. Innovations in photolithography, such as EUV technology, continue to push the boundaries of Moore's law, allowing for smaller, faster, and more powerful chips. This stage transforms the blank silicon wafer into a canvas of functional circuits, marking a significant step in the journey from raw material to a finished microchip. 4. Doping. Doping is a key step in the microchip manufacturing process where impurities are intentionally introduced into the silicon wafer to alter its electrical properties. This process creates the necessary P-type and N-type semiconductors that enable the formation of transistors, the building blocks of microchips. Enhancing conductivity, pure silicon is a poor conductor. By doping, its conductivity is improved to suit specific electronic functions. Creating semiconductors. Doping allows the creation of P-type positive and N-type negative semiconductors, critical for forming the junctions needed in diodes, transistors, and integrated circuits. N-type dopants, materials like phosphorus, arsenic, or antimony are added. These elements provide extra electrons, creating a negative charge carrier. P-type dopants, materials like boron or gallium are added. These elements create holes by accepting electrons, resulting in a positive charge carrier. Ion implantation. Ionized dopant atoms are accelerated and embedded into the silicon wafer at high speeds. This method allows precise control of doping levels and depth. Diffusion. The wafer is exposed to a high-temperature gas or solid containing the dopant. Dopant atoms diffuse into the silicon through thermal activation. After doping, the wafer undergoes annealing, a high-temperature treatment that activates the dopant atoms and repairs damage caused during the implantation process. This step ensures the dopants are electrically active and integrated into the silicon crystal lattice. Specific areas of the wafer are doped to form functional regions for transistors, such as source, drain, and gate terminals. Photolithography is used in tandem with doping to define precise regions for these modifications. Doping transforms the silicon wafer into a functional electronic substrate capable of switching and amplifying electrical signals. The ability to control doping at microscopic levels enables the creation of transistors as small as a few nanometers, a cornerstone of modern microchip speed and efficiency.
Deposition is a critical process in microchip manufacturing where thin layers of material are added to the silicon wafer. These layers form the insulating, conducting, or semiconducting materials needed to create the intricate structures and connections in microchips. The deposition process must be precise, as even slight variations can impact the chip's performance. Purpose of deposition: building layers. Adds the foundational layers for circuits, transistors, and interconnects. Insulation and conduction. Creates insulating barriers and conductive paths to enable the flow of electrical signals. Surface preparation. Ensures the wafer is ready for subsequent processes like photolithography and etching. Types of deposition methods. Physical vapor deposition, PVD. Materials are vaporized in a vacuum and condensed onto the wafer. Includes methods like sputtering and evaporation. Commonly used for depositing metals like aluminum or copper for electrical connections. Chemical vapor deposition, VD. Gaseous precursors react chemically on the wafer's surface to form a solid film. Ideal for depositing materials like silicon dioxide, SiO2, or silicon nitride, Si3 and 4. Variants include plasma-enhanced CVD, PEVD, for low-temperature applications. Atomic layer deposition, ALD, adds materials one atomic layer at a time through alternating chemical reactions. Provides exceptional thickness control for ultra-thin films. Commonly used for creating high-K dielectric layers in advanced microchips. Electrochemical deposition materials are deposited through electrochemical reactions, often used for metals like copper. Enables precise control over the thickness and coverage of conductive layers. Layer types and their functions. Insulating layers. Materials like silicon dioxide are used to electrically isolate different components on the wafer. Conductive layers. Metals such as aluminum, copper, or tungsten are deposited to form interconnects between transistors and circuits. Semiconductor layers, depositing additional layers of silicon or other semiconductors for specific functional regions. Challenges in deposition uniformity, ensuring the layer thickness is consistent across the entire wafer. Adhesion, layers must adhere well to the underlying surface to prevent defects. Contamination, any impurities during deposition can compromise the chip's functionality. Importance of deposition in microchip manufacturing. Deposition is foundational for building the layered architecture of microchips. The precision achieved in this process directly influences the chip's performance, energy efficiency, and reliability. As microchips continue to shrink, deposition techniques such as ALD are increasingly critical for creating nanometer-scale features. Deposition sets the stage for the subsequent processes of patterning and etching, where these layers are shaped into the microchip's functional components. Etching is a vital process in microchip manufacturing used to selectively remove materials from the wafer, shaping the intricate patterns of circuits and components. This step ensures that only desired areas of the deposited layers remain, creating the functional architecture of the microchip. Purpose of etching: removes unwanted material to refine the circuit patterns defined during photolithography. Creates trenches, holes, or other features necessary for microchip functionality. Ensures precise shaping of the wafer's layers to meet design specifications. Types of etching: wet etching. Uses liquid chemical solutions to dissolve unwanted materials. Commonly applied for materials like silicon dioxide or metals. Advantages: simple and cost-effective. Disadvantages: limited precision and control over feature dimensions. Dry etching uses gases and plasma to remove materials, offering higher precision. Techniques include reactive ion etching, RIE, combines chemical reactions and physical sputtering for precise material removal. Plasma etching utilizes ionized gases to etch materials with accuracy. Advantages: greater control for creating nanometer-scale features. Disadvantages: requires more advanced and expensive equipment. Ion beam etching. A highly precise technique that uses a focused beam of ions to physically remove material. Ideal for applications requiring extreme accuracy. Etching process steps. Preparation. The wafer is coated with a patterned photoresist layer that protects areas not to be etched. Material removal. Exposed areas of the wafer undergo etching to remove unwanted material while leaving protected areas intact. Photoresist stripping. After etching, the remaining photoresist is removed, revealing the finalized circuit pattern. Inspection. The etched wafer is inspected using advanced tools to ensure feature dimensions meet design specifications. Applications of etching transistor formation. Etching creates the detailed structures required for transistor operation. Interconnect creation forms pathways for electrical connections between circuit elements. Via formation, etches small holes to connect different layers of the microchip. Importance of etching in microchip manufacturing. Etching plays a critical role in translating circuit designs into physical structures on the wafer. The precision of the etching process directly impacts the microchip's performance, especially as feature sizes shrink to nanometer scales. Advances in etching techniques, such as atomic layer etching, AL, continue to enable the production of cutting-edge chips with higher densities and efficiencies. Etching complements processes like photolithography and deposition, shaping the microchip's final architecture and functionality. Metallization is the process of depositing metal layers on the silicon wafer to form the electrical connections, interconnects between transistors and other components in the microchip. These connections are critical for the microchip to transmit signals and function as a unified circuit. Purpose of metallization. Electrical interconnections creates conductive pathways for electrical signals to flow between various components of the microchip. Layer-to-layer connectivity establishes vertical connections between multiple layers of circuits in advanced microchips. Reducing resistance ensures minimal electrical resistance for efficient signal transmission. Metals used in metallization. Aluminum, historically the most common material due to its good conductivity and ease of deposition. Copper replaced aluminum in modern chips due to its superior electrical conductivity and reduced resistance. Requires a barrier layer, e.g. tantalum or titanium, to prevent diffusion into silicon. Tungsten, often used to fill small vias, vertical interconnects, because of its thermal and mechanical stability. Metallization techniques, physical vapor deposition, PVD. Sputtering or evaporation is used to deposit a thin metal layer, commonly used for initial layers or barrier metals. Chemical vapor deposition, CVD. Metal films are deposited through chemical reactions of vapor phase precursors, useful for conformal coatings and high aspect ratio features. Electroplating. A metal, usually copper, is deposited onto the wafer by immersing it in an electrolyte solution and applying an electric current. Ideal for creating thick metal layers required for modern high-performance chips. Process steps in metallization. Barrier layer deposition. A thin barrier layer, e.g. tantalum nitride, is applied to prevent metal diffusion into the silicon substrate. Metal layer deposition. A conductive metal layer is added using PVD, CVD, or electroplating. In copper interconnects, a seed layer is first deposited to initiate electroplating. Patterning, photolithography, and etching define the pathways and interconnect structures in the metal layer. Planarization. Chemical mechanical polishing, CMP, smooths the metal surface, ensuring even layers and preventing short circuits. Multi-level metallization. In advanced microchips, multiple layers of metal interconnects are required to accommodate complex circuits. Dielectric layers, e.g. silicon dioxide, are used to insulate metal layers from each other. Vias are etched into the dielectric layers and filled with metal to connect different layers. Importance of metallization in microchip manufacturing. Metallization is essential for microchip functionality, enabling efficient signal transmission and power distribution. The choice of metal and precision of the metallization process directly impact the chip's speed, reliability, and power consumption. Advances in metallization, such as the use of low-K dielectrics and copper interconnects, have revolutionized microchip performance, supporting the development of faster, smaller, and more efficient electronic devices.
8. Testing and packaging. Testing and packaging are the final stages of microchip manufacturing. These steps ensure that each microchip functions correctly and is protected from environmental damage, allowing it to be safely integrated into electronic devices. Testing the microchips, wafer-level testing objective, to identify functional and defective chips before the wafer is cut. Process. A probe card tests individual circuits on the wafer by applying electrical signals. Defective chips are marked for exclusion from further processing. Tools used. Automated testing equipment, ATE, with precision probes and sensors. Die level testing, conducted after the wafer is diced into individual chips. verifies the performance of individual microchips to ensure they meet design specifications. Burn-in testing simulates real-world operating conditions by running the chip at high voltages and temperatures, identifies early failures, and ensures long-term reliability. Functional testing ensures that each microchip performs its intended tasks, such as processing data or managing power. Packaging the microchips, die separation. The wafer is diced into individual chips, dies, using precision saws. Defective dies identified during testing are discarded. Each chip is enclosed in a protective package made of plastic, ceramic, or metal. The package protects the chip from physical damage, moisture, and contaminants. Wire bonding or flip chip bonding. Wire bonding, thin gold or copper wires connect the chip's contact pads to the package pins. Flip chip bonding. Solder bumps directly connect the chip to the package, enabling higher performance in advanced microchips. Sealing and marking. The package is sealed to prevent contamination. Identification marks, such as serial numbers or logos, are added to the package. Types of packaging. DIPE, dual inline package, used for simple circuits with pins arranged on two sides. QFP, quad flat package, features pins on all four sides, common in complex chips. BGA, ball grid array, used for high-performance chips with solder balls for dense connections. Final testing. Packaged chips undergo another round of testing to ensure they function correctly after packaging. Tests include thermal testing, verifies performance under varying temperatures. Electrical testing, confirms power consumption and signal integrity. Importance of testing and packaging. Testing ensures that only functional microchips reach consumers, minimizing the risk of device failures. Packaging provides durability, reliability, and compatibility with electronic systems, extending the lifespan of the chip. Advancements in testing and packaging technologies have enabled the creation of smaller, more powerful, and reliable chips, supporting the growing demands of modern electronics. These final steps are crucial for transforming raw silicon into the microchips that power our world. 9. Quality assurance. Quality assurance, QA, is a critical stage in microchip manufacturing that ensures the final products meet stringent performance, reliability, and durability standards. This process involves rigorous inspections, testing, and analysis at every stage of production to identify and eliminate defects. Purpose of quality assurance. Reliability. Ensure microchips can perform consistently under various conditions. Performance. Verify that chips meet design specifications for speed, power consumption, and functionality. Defect elimination. Identify and discard faulty chips before reaching the market. Compliance. Ensure adherence to industry standards and regulations such as ISO 9001 or JEDEC. QA steps in microchip manufacturing. Incoming material inspection. Raw materials, such as silicon wafers and chemicals, are inspected for purity and consistency. Suppliers are audited to ensure compliance with quality standards. Process monitoring. Each stage of the manufacturing process is monitored using statistical process control, SPC, to detect anomalies. Real-time data collection helps identify potential issues before they affect the product. Defect analysis. Microscopic and electron beam inspections are used to detect surface and structural defects in the wafer and circuits. Common tools include scanning electron microscopes, atomic force microscopes, AFM. Defects such as particles, voids, or improper doping are analyzed and mitigated. Functional testing conducted during and after fabrication to verify chip functionality and ensure it performs as intended. Includes power, signal integrity, and performance tests. Environmental testing simulates real-world conditions such as extreme temperatures, humidity, and vibrations to ensure reliability. Tests include thermal cycling, humidity resistance, electromagnetic interference, EMI testing. Failure analysis. Failed chips undergo detailed analysis to determine the root cause of defects. Results are used to improve manufacturing processes and prevent recurrence. Metrics used in QA yield rate, the percentage of functional chips from a batch. Defect density, the number of defects per unit area, measured in defects per square centimeter. Mean time to failure, MTTF, a measure of expected reliability over time. Continuous improvement QA teams work closely with process engineers to implement improvements based on defect analysis and testing results. Advanced machine learning and AI are increasingly used for predictive analytics, identifying potential issues before they occur. Importance of quality assurance. Quality assurance ensures that microchips meet the rigorous demands of modern applications, from consumer electronics to critical industries like aerospace and healthcare. By minimizing defects and maximizing reliability, QA safeguards the reputation of manufacturers and enhances end-user satisfaction. Future trends in microchip QA automation: use of robotic systems for consistent and efficient testing and inspections. AI and big data, leveraging analytics to predict and resolve issues in real time. Zero-defect manufacturing, aiming for near-perfect quality in every production cycle. QA is the backbone of the microchip industry, ensuring every chip that reaches the market is a testament to cutting-edge technology and precise engineering. 10. Final assembly. The final assembly stage in microchip manufacturing involves integrating the packaged chips into electronic devices or modules. This process transforms individual microchips into functional components ready for use in consumer products, industrial systems, or specialized equipment. Purpose of final assembly integration: combines the microchip with other electronic components to create a functional unit. Protection: ensures that chips are securely housed and protected from environmental factors. Testing: verifies the functionality of the assembled unit before deployment. Key steps in final assembly: board mounting. Microchips are placed onto printed circuit boards, PCBs, using automated systems. Techniques include surface mount technology, SMT, soldering chips directly onto the board, through-hole mounting. Components are inserted into drilled holes and soldered for robust connections. Placement is guided by precise machines to ensure accurate alignment. Soldering chips are soldered to the PCB to create electrical connections. Common soldering methods: reflow soldering, uses heat to melt solder paste, securing the chip to the board. Wave soldering, applies solder to multiple components simultaneously for through-hole mounting. Component integration, other necessary components, e.g. resistors, capacitors, connectors, are added to the assembly. Ensures compatibility and functionality of the complete module. Encapsulation and housing: assembled units are encased in protective housings to shield them from moisture, dust, and mechanical damage. For compact devices, miniaturized housings are used without compromising performance. System-level testing. The assembled unit undergoes rigorous testing to verify performance under real-world conditions. Tests include signal testing, thermal testing, power consumption analysis. Any defects identified are corrected before final deployment. Marking and labeling: labels are added to identify the product, including serial numbers, barcodes, and certifications. Marks indicate compliance with industry standards and regulatory requirements. Packaging for distribution. Final products are packed with anti-static materials to protect against electrical discharge during transport. Units are organized for bulk shipping or direct delivery to clients. Quality control and final assembly. Continuous inspections ensure that all components are correctly installed and operational. Faulty units are flagged for rework or scrapped to maintain quality standards. Statistical tools, like Six Sigma, are used to improve assembly accuracy and efficiency. Importance of final assembly. The final assembly process ensures that microchips are integrated seamlessly into end-use products. This stage bridges the gap between the microchip manufacturing process and real-world applications, guaranteeing that devices powered by these chips meet performance expectations. Conclusion. The creation of microchips is a remarkable blend of science, engineering, and precision manufacturing. From silicon wafers sourced from raw materials to the intricate processes of photolithography, doping, deposition, and etching, each step demands meticulous attention to detail. The microchips are then meticulously tested, packaged, and integrated into devices, ensuring they meet the highest standards of quality and reliability. As technology evolves, the manufacturing of microchips will continue to push boundaries, enabling faster, smaller, and more energy-efficient devices. Understanding the complex process behind these tiny marvels highlights not only their importance, but also the incredible expertise and effort required to produce them.